Hi, and welcome back. So, when last we talked, we were going over the ideas of the six pillars of data science. And as a quick refresher, we were talking about preparation and exploration, data representation and transformation, computing with data, data modeling, data visualization and presentation, and then the science about data science, so like the metadata science sort of thing. In this last topic, this last module within this overall question of what is data science, I want to get into the purpose of this class, and that is reproducibility and replicability. And I'll introduce a third topic called preproducibility shortly. So there's two key definitions here, and these are not the. This is kind of interesting. Currently, there's no consensus within science on what reproducibility means versus what replicability means. However, I'm gonna use these two definitions that were proposed. I think this is a paper that I saw off of well, it's in the National Library of Medicine, but I like these definitions. Now, that's not to say that in 5 years or 10 years we won't have a better understanding of what these terms mean for science, but this is what we're going to use for this class. So the replicability part of it is if we repeat a study. So the idea is we don't believe that a single experiment. So think back to the scientific method that you learned in middle school or high school, that you come up with a hypothesis, you generate some data, you test that hypothesis, and you repeat that process. And then if you can repeat it over and over and over again, then it becomes a theory and then it becomes a law. So if we can repeat a study, so a single study by itself is just a test of a single hypothesis, it does not become real scientific theory until it can be replicated and repeated multiple times by multiple independent people. Think about the idea of I've got a to-go spoon here. The a hypothesis of gravity. If I drop this spoon, it's going to fall every single time. That is me reproducing an experiment. Why? Because it's the exact same spoon, it's the exact same person, it's the exact same environment. I'm just dropping it over and over again. Now, replicability would be we either change, instead of dropping a spoon, we drop something else like this little cell phone holder, or if someone else came in and dropped the same spoon, or if I took the same spoon to a different environment. So we change something about it. We either we change who is running the experiment, we change maybe some of the parameters or the protocols of the experiment, or we change something about the data. That is, for us in data science, what we're going to term replicability. Okay. So that would be that a new study is added in this understanding of the hypothesis, and we need lots and lots of these new studies before a hypothesis could become a theory. And then and in longer terms, the idea of once something is a theory and it's been vetted for decades, if not hundreds of years, then it becomes a law. But reproducibility, that's going to be more of the focus of this class. Okay. Now, reproducibility would be where I am doing the exact same experiment by myself, and I write in my lab notebook exactly what I did so that someone could come and take the exact same spoon in the exact same environment. And I take measurements on, like, okay, what's the wind speed in my office? Am I running the fan or not, for instance? What's the temperature in my office? What's the humidity in my office? Exactly how many inches or centimeters above the desk did I drop this spoon from? Is it the exact same spoon? So the reproducibility side, this is all based on me providing very, very thorough documentation so that I can perform this experiment under the same conditions over and over and over again. And what this is doing is it's removing the probability that, oh, well, in one of these experiments, did I accidentally, instead of dropping a plastic spoon in a plastic wrapper, drop a spoon made out of a helium balloon, and then suddenly it floats up to the ceiling? Well, why? We understand that helium's light in the air. The helium balloon is going to float. But if we had just said spoon without clarifying that we mean a plastic to-go spoon in a plastic takeaway spoon in a plastic wrapper, then someone could interpret our experiment and say, well, clearly Dr. Odom is a fan of helium balloon animals, and he fashioned a spoon out of a helium balloon, like one of those balloon art kind of things that you see at children's carnivals or whatever. And he dropped it, and instead of falling to the table, it floated up to the ceiling. So reproducibility is all about the documentation. So I'm going to read these definitions again. So replicability, if we repeat a study with new data, okay? And so that's maybe a different PI, a different scientist at a different university, or perhaps it's the same scientist, but it's an entirely different environment, and you go and collect an entirely new cohort of data, something along those lines. Or perhaps you found a more representative sample. So yes, you got new data from the same environment, but you had better sampling design to make sure that the sample that you got was more representative of the population, something along those lines. That's all under the replicability because we have new data. And in those instances, in order for the hypothesis to be bolstered, we would need the results of that repetition should agree with the original results, or at minimum, not refute the original study's conclusions. So you could repeat a study in new data or in a new environment or a new something, and even if you don't reject the null hypothesis, it's not the end of the world. If the original study, they rejected the null hypothesis, but in this new study, we didn't reject the null hypothesis, then that probably just means that there was something about that original study that we're not understanding, some maybe a cohort analysis or whatever, and it means that we need to keep doing this, keep repeating it again. However, if we repeat this and suddenly we're getting the exact opposite effect, that every time we drop this spoon, it's floating up to the ceiling every single time, then that would tell us that there's a serious problem in our understanding of this scientific question. So reproducibility, this gets into what we are going to do in this class. And as a quote unquote rubber meets the road definition for us, definition of reproducibility is we repeat the same analysis. That means the same code, the same data set. We should be able to reproduce the published results. And I'm going to add the phrase exactly. All right. And this is a bit of a contentious topic because there are some things to say. We're like, okay, well, what if you use a Windows machine versus a Macintosh machine? What if you use a version of the code, like, because if you're using code packages, or a version of the operating system from 2 years ago, or versions of the R computing language from 2 years ago, or versions of the Python computing language from 2 years ago, will you get the exact same results if you change the software version, or if you change the package versions, or if you change the computer, that sort of thing? Again, that's a little bit into the gray area, getting a little bit into the weeds, but the general idea remains that if we start with the same data and we apply the same code to that same data, we should be able to get almost the exact same results that were published in whatever this original paper was. That if we found an effect size of 0.8, then we should be able to run that same code on that same data and get an effect size of 0.8 every single time. Again, this is different from replicability, because replicability, it could be a new data set, new experiment, and so it would be highly unlikely to get an effect size of exactly 0.8 again. That's not what we're after. That's not what we're after in this class. Replicability is not what we're talking about, but we are talking about reproducibility. That if I take the exact same data and I apply the exact same procedure to that same data, I should get the exact same results. And in order for us to be successful in this endeavor, we have to use code. We cannot just rely on someone writing, 3 or 4 sentences in their manuscript saying, "Oh, we did logistic regression in R, and this is the results," or whatever, and we imputed missing values with MCV or whatever. That is not enough. there could be, and it's honestly kind of funny. There are so many ways for that to go wrong or that to go different. And this is where we get into this idea of the reproducibility crisis. Um, and in public health, I don't know that there's much metadata science results published in public health, but in oncology specifically, because this is, I did my postdoc in doing like biostats and statistical genetics at a cancer center. So this idea of the reproducibility of oncology papers, this is huge for us that we've spent. So 53 published articles. If you think each published article cost $1 million to $2 million, is $100 million there that were spent, and only 6 of the 53 were reproducible, where there was enough information in the paper for someone to come back and say, okay, we're going to rerun this with, given the same exact data, we're going to rerun the same experiment and get the same results. Only 6 of those 53 was that the case for. Okay, that means for the other 47 papers did not provide enough information. Let me turn off my notifications real quick. I apologize. So the other 47 papers did not provide enough information in their methods section for someone independent to come behind them and say, let's see if we can repeat these results, to see if we can reproduce what they did. Psychology, similar story here. Pharmacology, similar story. Now, this guy, John Ioannidis, he's a bit of a he's a character. Some people love him, some people hate him. I like a lot of what he stands for in terms of trying to push people towards reproducibility. He has some very interesting takes on the science of the COVID-19 pandemic. And for that, I can't just carte blanche take everything he says at his word, but he has done a lot of research on why we're not seeing the science replicate and why we're not seeing science move forward because of that. So if you think about it, back to the scientific method, if we have a hypothesis and we publish this paper saying, oh, we reject this hypothesis or fail to reject this hypothesis or something, that adds information to the science. And someone's going to come behind it and say, I'm going to try to replicate this so that we're adding strength to this hypothesis. But if people can't replicate it, then that means we're just in this cycle of constantly generating and testing new hypotheses without those new hypotheses getting built up into theories. And therefore, we can't understand what's really going on if we're stuck in this cycle of propose a new hypothesis, test the new hypothesis, and back and forth, back and forth, back and forth, because the published results from testing these hypotheses aren't replicable. So anyway, there's some papers here. I recommend that you at least read the abstracts of them just to kind of get the idea of what's going on. Now, Phil Stark, he's at Berkeley. He had a phrase, and that was before reproducibility. So that's before someone else could come behind you and take your data and your code and get it to run, must come pre-producibility. And that's the idea that you yourself can start with your data and your code and like wipe your computer from scratch, go to a brand new computer with everything else, and start over from scratch, import that data set, run the code, and get the exact same results. This is the idea of pre-producibility. And so his quote is, instead of arguing about whether results hold up, instead, we should be pushing for people to share enough information to allow a, quote, dedicated reader, okay, to repeat the calculations in the paper. So this idea of a dedicated reader, that's someone who's not just taking the results at face value, but is really trying to understand what's going on in this paper. And they say, okay, well, the data was published as supplementary material to this paper. The code was published as supplemental material to this paper. Can I take the data that they published and the code that they published and rebuild table 1 and table 2 and the results figure and whatnot? So that's the idea that would be the reproducibility part, that someone else could come behind you and take your code and take your data and your code and reproduce the tables or figures in your paper. However, before that's ever possible, there must be this idea of pre-producibility, that you yourself can start over, kind of wipe your slate clean, start over with your data, start over with your code, and get the same tables and results for your manuscript. So if you want this to work, you have to use computer code. You can't simply write in English what you did. All right. And think to the idea of doing like a lab notebook in biology. If you wanted someone else to be able to reproduce your experiment, you had to take meticulous notes, incredibly detailed, incredibly meticulous notes, and draw good pictures as much as you possibly could. All right. Code, in terms of like an R script or a Quarto document or something like that, is basically the lab notebook of any computational study. So if you're working with ACS data, or you're working with ABCD data, or you're working with I don't know what other, so many other, the Ryan White HIV data, you need to have a very, very good lab notebook, if you will, where you say, this is how I did what I did. And that lab notebook really needs to be code. Okay. All right. So I want to, like, right here, this is where I want to kind of talk you through. I'm assuming that all of you have the time to try to meet with me individually and go through the steps of getting R and RStudio installed. I'm not gonna walk you through this. This information is here, and especially during the first week of class, I want to spend some time making sure that everybody has R and RStudio downloaded and installed appropriately on their computers. And that's something that I can't really, if I just make a video of it, there's going to be so many different ways that it could go wrong that in my experience, it's often not worth it. But try to go through these steps. And for most of you, it will just work. For about 10% of you, something will go wrong. And it'll be something set up on your computer incorrectly, or somehow computers, there's a ghost in the machine, if you will. Things just go haywire sometimes. You have to be patient. You have to say, okay, well, how much of this is me, I'm doing the wrong steps, versus how much of this is my computer just acting crazy. So anyway, these are some steps for downloading and installing R. And this window, once you get R and RStudio, you should be able to open RStudio and see a window that looks kind of like this. This version is from, oh God, this is 4 years ago now, version 3.6. Obviously, your number and your date and this name right here will be a bit different. We should be on 4 point, what's that, 4 point, I don't remember, 4 point something now. But I do want us to see, and I'll show you kind of what mine looks like. So this is, let me go back over here to File. So this is kind of like this fresh, open installation of RStudio. Nothing's here, and some of you in a previous video we said hello, and we had the computer tell us hello back. In computer science, this is often called a hello world statement. So in R, the way we would type a simple command, we go down right here. This is called the console. We see our cursor blinking right here. This is where we type commands for the computer to do something. And so I type, not if I could spell correctly, hello world. Okay. And this will be my first code in R. If you've already typed hello and gotten it to run, that's cool. If not, this may be your very first code in R. And if I want the computer to actually execute this line of code, i.e. do what it's telling me to do, or do what I'm telling the computer to do, what I'm actually telling the computer is I'm using this quote symbol right here to say, write a message. And whatever goes between the quotes, so here's the opening quote, and here's the closing quote right here, whatever goes into the message, display it back to me. And here we have it. We have our message from our computer. We told our computer, tell the world hello, and the computer tells the world hello. And this will be all for where we are right now. In the next video, we'll go through exactly what all is going on in this moderately complicated window. So we'll see you soon.